Hello students, how are you? I welcome all of you on this educational platform, and I hope and we pray that you are safe and well at your home. In today's session, we will discuss about the periodic properties. Any periodic property we will discuss over the 4 parameters. Number 1, what is periodic property? Number 2, what are the factors which affect this periodic property? Number 3, what is the variation across the period and down the group in the periodic table? And number 4 is the exception. So in today's class, we shall discuss about the 2 periodic properties, that is atomic radius and ionization potential. And both of them are very important for examination point of view. So let's start them.
So students, in the previous unit, I told you about the periodic classification, genesis of the periodic table, and also about the modern periodic table. In this today's session, I'll tell you about the atomic radius. I'll tell you about the atomic radius in detail and also about the ionization potential, in short, also called as IP. So, what do you mean by trend in physical properties? Why we classified the periodic table? Why we classified the elements? Because we wanted to study the elements in a particular trend. So we will discuss the periodic trend in physical properties with respect to atomic radius and also with respect to ionic radius in this chapter, in today's session. So what is atomic radius? As per the definition, it is distance between the center of the nucleus to the outermost shell or the outermost electron. So whatever the distance between center of the nucleus, which is here, right here in the middle, to the outer electron, which is present in the outermost shell. So this distance, which is from outer electron to the center of nucleus, is called as atomic radius. So this is atomic radius, guys. And it is very small in size, and it is measured in picometer. You know what is picometer? 10 to the power minus 12 meter, or the angstrom. Angstrom is 10 to the power minus 10 meter, and nanometer you must be knowing, 10 to the power minus 9 meter. So they are very small in size. So they are measured in these small units. And you must be thinking that, sir, if they are that small, how we can measure them? So they are measured by the special techniques called as X-ray diffraction or the spectroscopic method, in which we use spectrographs, which you will study in the higher classes. So what are the type of the atomic radii? How many type of atomic radiuses are there? So based on the nature of the bond, atomic radius are of following type. Number 1 is atomic radius, which is further classified in the covalent radius, metallic radius, and van der Waals radius. What is covalent radius? Which is there in the covalent bond. What do you understand by the metallic radius? It will be there in the metals and alloys. And van der Waals, you must be knowing that van der Waals bond is the weakest possible bond between the atoms or sometimes molecule. So the radius which is present in the van der Waals molecule is called as van der Waals radius. Now we shall discuss them one after one. First is the covalent radius. So what is the covalent radius? You tell me, what is covalent bond? In the covalent bond, there is a sharing of electron between two atoms. So half of the distance between the nucleus of two covalently bonded atoms, which are bonded with each other with a covalent bond, are called as covalent molecule. And when the elements are same, when the bond is formed between similar elements, like in this example, you see bond is formed between chlorine and chlorine, and the distance between them is 198 picometer. So this is 198 picometer distance between them, and half of this distance is 99 picometer, and this is called as covalent radius. So here is the covalent radius. Now another one is metallic radius. So where we calculate the metallic radius? We calculate the metallic radius in metals and also in alloy. You know what is alloy? Mixture of metal is called as alloy. So in the metallic radius, half of the internuclear distance, whatever the internuclear distance between the nucleus of the two adjacent atom in the packing of metal, which is called as metallic crystal. You know, SCC, BCC, FCC is called as metallic radius. Say for example, what about the metallic radius of copper? Now you see we have two different atoms of copper. In these two different atoms of copper, the distance between their nucleus is 256 picometer. Out of this 256 picometer, what is their half? Is 128 picometer, which is metallic radius of copper. Then van der Waals radius. It is half of the distance between the nucleus of two adjacent identical atoms belonging to the neighboring molecule of an element in the solid state. So, you know, in the solid state, when there is a van der Waals bond between the similar atoms or molecules, say for example, this is oxygen. This is one molecule of oxygen and here is another molecule of oxygen. So in this oxygen, there is a covalent bond. Here is the covalent bond. But what bond is present in between these two molecules is van der Waals bond. So wherever van der Waals bond is there, half of the distance between them is called as van der Waals radius. So van der Waals radius in the chlorine molecule. Now you see, this is chlorine, this is another chlorine. There is a formation of covalent bond between them. This bond is covalent. This is covalent bond. Similarly, this bond is also covalent, sharing of electron. But what about in between them? In between them, there is a formation of van der Waals bond, and the distance is 3.72 angstrom in case of chlorine. So half of this distance, which is 1.86 angstrom, is the van der Waals radius of chlorine. So you see, this is the van der Waals radius of chlorine molecule. I hope you understand what is covalent radius, metallic radius and van der Waals radius. Now what about the atomic radius in a period? What happens with the atomic radius in a period? What do you think? See, when we go left to right in the period, shell remains same, number of shell is same, but atomic number increases. Because of the increase in atomic number, there is a continued increase in the nuclear charge. So across the period, outer electrons are in the same valence shell and nuclear charge increases while the shell remains same, resulting in the increased force of attraction on the electrons. And it is very clear, whenever there is an increased force of attraction over the electrons by the nucleus, there will be decrease in size. So as the nuclear charge increases, atomic radius decreases across the period from left to right. So when we go left to right in any period, atomic radius decreases. So this is the trend of atomic radius of elements. Here is the data of the atomic radius of second period members: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. And you see the size in their radius. Although in the end of period there is a slight increase in size because of the van der Waals radius, but these are the values. You see, there is a significant decrease. There is a significant decrease in the atomic radius when you go left to right in the periodic table across the period. But what about the atomic radius in a group? What do you think? In the group, whether the atomic radius increases or it decreases? What happens with the atomic radius in a group? See, in the group, atomic radius increases. Why increases? Because in the group, there is an increase in the number of shell. As you go down the group, shell constantly increases. So number of shell, number of orbits, it increases down the group continuously, and change in the shell is a very big factor which influence the atomic radius, because for higher shells atomic radius is more. So when we go down the group, atomic radius increases, and here is the figure. In the family first A, alkali metal, when we go down the group, you see there is a constant increase in size. Atomic radius increases constantly. So finally we can say that atomic radius is inversely proportional to nuclear charge. If you will increase the nuclear charge, there will be decrease in the atomic radius, and also atomic radius is proportional to number of shell. When number of shell increases, atomic radius also increases. With the increase in number of shell, atomic radius increases, and it is very clear and very easy to understand. If you increase shell from 1 to 2, radius will increase. If you increase shell from 2 to 3, radius will increase, and from 3 to 4, radius will definitely increase. But this was the atomic radius. What about the ionic radius? See, how many type of ions do we know? In the ionic radius, what it is the effective distance from the center of nucleus of the ion to the outer electron. And how ions are formed? Ions are formed when either we gain electron or we lose electron. See, if we lose electron, then there is a formation of cation. So cations are formed by the loss of electron. So when a neutral atom loses electron, maybe one or more, then there is a formation of cation. And when something is lost from any atom or species, definitely size will be smaller than the neutral atom. And when we form anion, which is formed by the gain of electron, so here we gain electron and here we lose electron. By losing something, size decreases, and by gaining something, size increases. So it is quite easy to understand that radius of cation will be smaller than the neutral atom, and radius of anion will be larger than the neutral atom. Suppose you have neutral atom oxygen, and you have species O plus, and you have another species O minus, then this will be the order of size. O plus will be the smaller one, then O, and the biggest is O minus. This is the order of size. Atomic radius, ionic radius moreover. What is lanthanide contraction? There is a decrease in size of the atoms or the ions m plus 3 with the increase in the atomic number among the lanthanoids. This is quite famous by the name of lanthanoid contraction. And there is one exception of EU and YB, when there is a not decrease in the size. So the question is, why lanthanoid contraction occurs? Why is this contraction occurs? This occurs because of the poor shielding effect, and you see there is a constant decrease in the radius. There is a constant decrease in the radius. Leave the exceptions. Constant decrease in the radius called as contraction. Decrease in the size, radius is contraction. So this is called as lanthanoid contraction. Now we shall discuss about the ionization enthalpy. After discussing radius, now we shall discuss ionization energy or the ionization enthalpy. So what is ionization? In the simpler terms, ionization is the attainment of charge. When we remove electron from any species, in the broad terms, when we remove electron from species, this is called as ionization. Now specifically, it is quantitatively measured by the tendency of an element to lose electron. So basically IP, that which is ionization potential or ionization energy, it quantitatively measures the tendency of element to lose electron. If IP is more, means electron is not released easily, means this species will not release electron easily. But if IP is less, means this particular element is having more tendency to release electron and will release electron easily. So the units of ionization energy is simply kilojoule per mole or kilocalorie per mole, or sometimes electron volt per mole, because energy in terms of the electron is very less, so you also represent it in the electron volt, in the terms of electron volt. And here is the conversion. 1 electron volt per atom is equal to the 96.5 somewhat kilojoule per mole, or 23.06 kilocalorie per mole. What is first IP? What is first ionization energy? When you remove 1 electron from the atom is called as ionization energy. So it is minimum energy required to remove electron from the outermost orbit shell of an isolated gaseous neutral atom. When you remove electron from the isolated gaseous and of course neutral atom, this is called as first ionization energy. So we need isolated. You cannot remove electron from the molecule. In order to define the ionization energy, we need gaseous atoms, also neutral. See for example this one. We have this X gas. Now this is isolated. It is not X2. X2 is molecule. So if you are using molecule, it is wrong. X is isolated atom, and 1 electron is being removed from this is called as ionization energy. Now what about second ionization energy? Before I told you about the second ionization energy, what do you think of second ionization energy? You should give it a thought. Now what you are thinking? So this second ionization energy is the required energy to remove the second electron, which is now loosely bound after removal of the first electron. It is not neutral anymore. It is now unipositive ion. It already attained the positive charge, and now you are about to remove second electron from this, and that is called as second ionization enthalpy. Now you see in this example, now this species is not neutral anymore because 1 electron is already been removed from this, and now we are about to remove the second electron. This is the second electron which is being removed from the species X. So in order to remove the second electron, whatever energy required is called as ionization enthalpy. In general, this energy is always required to remove electron from atom or ion. So ionization enthalpy is always positive because it is required energy, or you say this process is endothermic in nature because this energy is always required. It is never a released energy. It is always a required energy. So what are the factors which affect the ionization potential? The first factor is atomic size. What happens when atomic size increases? See, it is easy to remove electron from the large atoms because in the large atoms, attraction of nucleus towards the outer electron is more if it is smaller in size. But what about the larger atom? For the larger atom, there is a distance between center of nucleus to the outer electron. So the effective nuclear charge is more for the smaller atom. That is the reason why it is difficult to remove electron from the smaller atom. And as a result, in conclusion, we say as the atomic size increases, IP value decreases. It becomes easy to remove electron from the large size atom. So finally, we can say IP is proportional to 1 upon atomic radius. Second is the nuclear charge. Before I proceed further, you tell me, what is nuclear charge? The positive charge which is present inside the nucleus, center of the atom, is nuclear charge. More nuclear charge in center, more will be the value of IP. So the nuclear charge increases, IP value also increases. There is a directly proportional ratio. So IP is directly proportional to the nuclear charge, sometimes indicated by Z. So whenever Z, or you say nuclear charge, increases, value of IP also increases. The third factor is screening effect. Students, what is screening effect? See, inner electrons also try to repel the outer electron, which comes, this repulsion of the inner electron to the outer electron comes a kind of screen in the nuclear attraction. So it is called as screening effect. In easier terms, you can understand screening effect as a repulsion of inner electron to the outer electron. See, in any atom, if this is outer electron, then these are the remaining electron, including remaining electron of the outer shell and other inner electron. These electron collectively give repulsion to this outer electron because there is a repulsion between similar charge, is called as screening effect. Now we can understand, if the screening effect increases, which is repulsion of the inner electrons to the outer one, definitely size will increase. And if the size will increase, it will be easier to remove electron. So IP is proportional to 1 upon screening effect. Greater the screening effect, lesser will be the value of IP. The fourth factor which affect the IP is penetration power. See, in the different shells and subshells, they are not at the same distance from the nucleus. They are at the different distances from the nucleus. S subshell is closest to the nucleus. So definitely it is more difficult to remove electron from the S subshell. And technically we say that penetration power of S subshell is maximum. So it is maximum difficult. It is most difficult to remove electron from S subshell rather than P subshell or D subshell or F subshell of the same orbital. And technically we say that with the increase in penetration power, IP increases. And the next factor is electronic configuration. See, whenever electronic configuration is stable, what do you mean by stable configuration? Either they are half filled or fully filled. So in terms of the for the P subshell, half filled is P3 and full filled is P6. So when we have half filled or full filled orbitals, then they are stable and it is difficult to remove electron from the stable configuration. This is the reason why IP is more for half filled or full filled electronic configurations. So IP of nitrogen is more than IP of oxygen. Although size of oxygen is smaller than nitrogen, but still IP of nitrogen is more than nitrogen just because of the P3 configuration of nitrogen, while in oxygen the configuration is P4. So it is, again, remember that it is difficult to remove electron from the stable configurations. So this is the trend in the ionization potential. This is the trend and variation of the ionization enthalpy of the atomic number 1 to 60. Here you go. So this is how ionization energy changes from the element 1 to 60. Now one more question is there, what is the trend? The trend in the ionization energy is, in the period, IP increases as we go left to right, because size decreases, IP increases. So when we go left to right, there is a decrease in size and obviously increase in ionization potential. Here is the reason: decrease size and increase in effective nuclear Z. But what about the group? In the group, IP decreases as we go down the group, and the reason is atomic size increases and effective nuclear charge decreases. So when we go down the group, there is a decrease in the ionization potential. So students, this was all about the ionization potential. In the coming classes, we will tell you about the more periodic properties. I hope you liked today's lecture. Please keep coming and keep studying and keep educating yourself.